All right, welcome, welcome, my Math 70s. We are gonna go over Chapter 8 problems from the Exam 2 review today. That is going to start with 8.1. I'll go ahead and write the ones that I'm gonna do out here, just so you have an idea. So today, I hope to get through all of this. If not, we can come back and finish this up a little bit on Thursday. But section 8.1, number 13 and 15, these are book problems. Section 8.2, 5 and 8. Section 8.3, there's going to be the hydrostatic force portion, which is number 2 and 8. And section 8.3, the center of mass and centroid part. Oops. Centroid, which will cover problems 23 and 29. Oops, oh well, okay. Let me save that picture and then I'm gonna go ahead and clear this out. I'll have this video available on YouTube. Okay, clear. So the first one that we're gonna start with is section 8.1, number 13. The problem prompt asks for us to, forgive me, I'm gonna have to go back and forth between this mouse and this graphic tablet device, which I'm still getting used to. So we're asked to find the exact length of the curve. Remember, 8.1 is arc length. So I'm gonna go ahead and do a new share of a whiteboard and then blow that up and try to move this out of the way. All right, so section 8.1, number 13, I wanna change that to black. I'm gonna find arc length. And the curve that we are given is x equals 1/3 square root y times the quantity y minus 3. And that's for y being between 1 and 9. Okay. So let's take a moment to remember the arc length formula. In this case, we're going to be taking the integral over y. So our length will be equal to bounds c to d. And then we're going to have the square root of 1 plus the quantity g prime y, excuse me, squared, and then dy outside. So for this part, I would definitely suggest graphing what you have first. You will have access to your computers and stuff a little more freely than I would normally have for your tests and quizzes and things. So just be mindful that even if you are looking up what the formulas look like and what the graphs look like, you do want to know how to make these graphs by hand. So essentially, first thing, for the graph, I'll do my best on this. You can just make a table of x and y values. We know y is going to go from 1 to 9, so we can put some values in the middle to just try to check what would happen with that. So I chose 4 because that'll give us a nice root. And then I also just chose 6. It won't give us quite a nice root, but we can just plug it into a calculator. So remember, you're going to just take these y values and then plug them into this function here, and then you're going to get an x value out. So let me write out what we get here. We get a negative 2/3, positive 2/3. For this one, it's approximation about 2.45. And then for 9, x comes out to be 6. So let's see if I can make this without it being too janky. Let's see, this is going to be y and x. This is 10 and 10. And you're going to have a curve that looks something like Let's try a little higher. That is so ugly. Didn't come out quite the way I'd hoped. Let's see, 6 would be about here, and 9's here. So we're gonna get a curve sort of like this. Okay, so this is x equals g of y. Okay, so what we're gonna do now, we're gonna find g prime of y so that we can plug that into here. G prime, you're gonna be taking the derivative of 1/3 times y to the 1/2. Remember that's square root y. And then you're gonna have y minus 3, the quantity next door. And that comes out to be 1/3 times, let's see. So I just essentially factored out a 1/3. And then from here, we get y to the 3/2 minus 3y 1/2 prime. Okay, so I factored out my 1/3, and then I went ahead and distributed the y to the 1/2 in here to get to this step. Okay, so now I'm going to keep the 1/3 and then actually take the derivative. We get 3/2 y to the 1/2 minus 3/2 y to the negative 1/2. Okay, and then we can go ahead and distribute the 1/3 in. We're going to get 1/2 y to the 1/2 minus 1/2 y to the negative 1/2. So this is our g prime y. Okay, so also let me make some emphasis with the bounds here. Your bounds are given here for y. So when you create your integral L, that'll be the integral from C to D, which is 1 to 9. You're going to have your square root, and then 1 plus, and g prime of y is going to go in here. And then via our formula, we're going to be squaring that. Okay. So what I'm going to do, I'm actually going to break down the gy prime part squared and then add 1 to that, and then I'll go back and plug it in. So I'm going to go ahead and save this screen. And then I am going to clear this side portion here. Bear with me here, it takes a little while. And remember, I'll have this video up so you don't really need to worry about missing any details. All right, so let's go ahead and look at the quantity g prime y squared. That would be the quantity 1/2 y to the 1/2 minus 1/2 y to the negative 1/2 squared. I'm going to go ahead and factor out a 1/2 inside the brackets. I have y to the 1/2 minus y to the negative 1/2 left over, and then I still have squared outside the brackets. So remember, that means I'm going to be squaring the 1/2 separately from the factor that I just wrote. And then I'm going to expand this factor. So this is going to be, and let me kind of go into a little bit of detail here. So we have y to the 1/2. That quantity would be squared. We have a subtraction of 2 times y to the 1/2 times y to the negative 1/2. And then we're adding y to the negative 1/2 squared. Now you wouldn't need to write it this way. You can just do a traditional FOIL on this. Remember, you're really taking this factor and multiplying it twice. All right, so what this comes out to is 1/4 times the quantity y minus 2 plus y to the negative 1. You could leave this as a fraction if you like. I don't like to do my integrals and derivatives with fractions, okay? All right, so we have our g prime y squared. So now what we're going to do, we're going to add 1 to that. So that's 1. And then you have plus, I'm going to go ahead and distribute the 1/4 to each of the items in this big factor here. So I have a 1/4 y minus 1/2 plus 1/4 y to the negative 1. I have like terms here. So that's going to give me, that part is going to be 1/2, but I'm going to put the 1/4 y first. And then to make things a little bit smoother so I don't have to worry about the fraction, I'm going to pull the 1/4 out. And then what I have left over is y plus 2 plus y to the negative 1. And you can check that by distributing back and making sure you get the same thing up here. So let me save that picture. I'm going to go ahead and clear this out. Let me clear just the top portion again. Bear with me here. So before I forget, let me go ahead and put the 1 plus g prime y squared up here. And clear the rest. Okay, so essentially what I'm going to be doing for this next part, we discussed this in class before, but you might have forgotten. It's kind of an algebra thing. Right here, this part, y plus 2 plus y to the negative 1 is actually a perfect square trinomial. Okay. So what that is, y to the 1/2, the quantity squared, essentially taking the square root of this part and putting it in here and squaring that. And then we're going to have a plus 2 times y to the 1/2. Over here, if we took the square root of y to the negative 1, that would be y to the negative 1/2. That looked ugly. And one more thing. Come on. Okay, and then we're also going to be adding y to the negative 1/2 squared. If that part's still confusing to you, just ask me about it. I can go over it in a little bit more detail. So if you actually look at these parts, this would be y. This part simplifies to 2. This part simplifies to y to the negative 1. Now from this formula, what you get, some quantity squared. This first portion, y to the 1/2. This last portion, y to the negative 1/2. And in the middle, there's a positive, so it'd be plus between. Okay, so what we wind up getting for 1 plus g prime y squared, it's going to be 1/4 times what we just had up there. Okay. So then we're actually ready to find our arc length. This means L be equal to the integral from 1 to 9. We're going to have our, remember we had the square root of 1 plus g prime squared. So that's the 1/4 times the quantity y to the 1/2 plus y to the negative 1/2 squared. dy. Okay. So then from here, we can remember the 1/4, when you take the square root, that's going to be a 1/2. You still have your bounds out here. I'm not going to switch back this time to the different color. And then if you take the square root of this perfect square here, you get y to the 1/2 plus y to the negative 1/2. Okay. Before I continue, let me go ahead and save this picture, and then I'm going to clear it out. Let me rewrite. I wonder if I can, I'm going to try something real quick, see if I can select this and then move it up. Yay! I just found out how to do something new, y'all. All right. Saves time. Okay, so I'm going to go ahead and continue with the integration. You have 1/2. We can go ahead and take the integral of these items individually. We're going to have y to the 3/2 with a 2/3 in front. And then we're going to be adding, remember I generally say with power rule, just start with the variable and what the power would go to. So add 1 to this. And then just put the reciprocal in front. It'd be 2/1, so we'll put a 2 in front. And then it is a definite integral, so we have our bounds. Don't need to add c. And then we're going to go ahead and evaluate this. So just to save some time, I'm just going to go ahead and put ... here, and then put what you should get for your actual length. If you need help with the intermediate steps, just ask me and I can go over those with you. I have them written out. Okay, and this one's already been checked. So save. And that is the end of 8.1, number 13. Before I get into any questions, I'm going to go ahead and clear this out. And I'm going to start 8.1, number 15, go through that. And then I will ask you guys if you have any questions for me. So let me clear drawings. Okay. So the next one is section 8.1. Number 15. We are also looking for arc length again. And this time we're given y equals ln of secant x. And we have bounds 0 to pi over 4 for x. So for this one, since we're integrating over x, the arc length formula we're going to be using, L is equal to, we have our bounds a to b, and then we have square root 1 plus f prime of x squared dx. Again, with the graphing, so this time I'm going to make my XY chart. And then I'm choosing X values now and getting out Y. So the X values I chose, the way that I did this, essentially I know that if I have 0 to pi over 4, I can take averages to get middle values. So one way I did it, and I can explain this in further detail if you need later. This is 0 pi over 16. This is 4 pi over 16. In the middle will be 2 pi over 16. Which would be the same as pi over 8 if you took an average. And then if I count up, so 0 pi over 6, 16, pi over 16, 2 pi over 16, 3 pi over 16, and 4 pi over 16. Okay, so 0 pi over 16, pi over 8, 3 pi over 16, and pi over 4 are the X values I'm going to use here. And then when I plug them in, I get 0. I'm doing approximations for these. I get about 0.02, about 0.08, about 0.18, and about 0.35. Since 0 is my lowest X value, I can just make a quadrant 1. Graph. So this would be pi over 4 here. And those are the other values I found up here. And then the highest value we go up to is 0.35. So I'm going to count 1, 0.2, 0.3. Let me try doing this graph in another color. We'll see if it works out well. Red. So it looks something like this. That's so ugly, but bear with me. I'm still learning how to use this. So this would be your function f of x. Okay, so now what we're going to do, this part's just to help you see what the graph looks like and what you're integrating over. So integrating with respect to x. So we're making little strips this way, vertically. All right, so what we're going to start with, similarly to the last problem, is f prime of x. That's going to be ln of secant x prime. You're going to need to use chain rule here. We have 1 over secant x from the derivative of ln, and then you're going to multiply by the derivative of secant x, which is secant x tangent x. And then when you simplify that, it comes out to tangent x. Okay. So let's go ahead and figure out what f prime x squared will be. That would be tangent x squared. which could also be written as tangent squared x. And then let's go ahead and figure out what 1 plus f prime x squared will be. So we're going to have 1 plus tangent squared x. And remember, that's an identity, trig identity. This actually would come out to secant squared x. Okay, so let me go ahead and save that portion. Essentially, what we're going to be doing is plugging in this portion right here. Okay. Let me go ahead and clear this out. Okay, and go ahead and start integrating. So L, your arc length, equal to, let's do our bounds in a different color so we remember where they come from. Come from right here. So 0 to pi over 4 for x values. And then radical, we found out that the 1 plus f prime squared is secant squared x. And dx. Okay. All right, so then from here, integral 0 to pi over 4, this part here would become absolute value of secant x dx. Again, remember, you would need to write this portion to show it and like be graded on that part. As long as you note, you'll get the secant x from that. Essentially, we're already dealing with positive secant values, right, with our bounds. Okay, and then from here, the integral of secant x, I wouldn't expect you to actually like tear this apart and show this formally, like for this type of problem. I'm testing you on arc length. So for this one, you could check a chart if you wanted to. This would be ln of the absolute value secant x plus tangent x, evaluated from 0 to pi over 4. And then plug in. Okay, and then for this part, let me show what these things turn into. You can draw out, like if you needed to, draw out your unit circle and think like this is the reciprocal function of cosine. So cosine of pi over 4 is root 2 over 2, which means secant of pi over 4 will be its reciprocal. Root 2 is what it simplifies to. Tangent of pi over 4, that's going to be 1. Secant of 0, that's going to be 1. And tangent of 0 will be 0. Okay. So we have ln of root 2 plus 1. And then for this part, this would become ln of 1, which is equal to 0. So this whole portion cancels out here, right? So your arc length, let me save that piece so that I can make it neater because we have an absolute value here and root 2 plus 1 is going to be positive. So we can drop the absolute value. Okay, I'm going to go ahead and clear this out. Takes a little while. Okay, so what we find is that L will be equal to ln of root 2 plus 1. Save that picture. All right, so that takes us through 8.1. I'm going to go ahead and pause the recording so that you guys can ask questions if you have them. Hold on one second. Okay, so right now you guys should be seeing 8.2 on the screen. I'm going to cover 8.2 number 5 to begin, and then I'm going to cover 8.2 number 8. So 8.2 number 5, we are asked to set up an integral for the area of the surface obtained by rotating the curve about the x and y axes individually. And then we're going to use numerical integration. So for this part, you could use like Wolfram Alpha or EMAP help or whatever in order to figure out what the evaluated integrals would come out to. So I'm going to start with number 5. Okay. So let's go ahead and do a whiteboard share. Clear this stuff out and blow this up. Okay, so section 8.2 number 5 is a surface area. We are given x equals y plus y to the third, and integrating from y equals 0 to 1. So essentially for part A1, it's x-axis rotation. Remember that the formula for x-axis rotation, you have the surface area. You're going to have A to B, 2 pi y ds. Okay. Oh, in this case, let me be a little more meticulous. I wouldn't like fault you for this or anything, as long as you know that these are the bounds. But since it's going to be integrated in terms of y, I'm going to put a c to d here. Okay. So the first thing you'd want to do is have an idea of what the graph looks like. So for that, same thing, set up a table and graph to the best of your abilities, x and y. For this one, we'd plug y values in and get an x out. So I just broke up between y being from 0 to 1. Use some middle values. I used 1/4, 1/2, and 3/4. Averages again. And then the x values I get from that, I get 0. I get an approximation of 0.27, an approximation of 0.63, approximation of 1.17, and 2. So your general graph will look something like this. Let's see. Okay. And actually, let me do it in a different color. Okay. So this is your function. X equals gy. That is so small. Hold up. Easier. Okay. All right. So for this first part, we're rotating that piece of the curve about the x-axis. So let's see if I can experiment a little bit more. Oops, let's try that. Okay. Essentially rotating like this. Okay. So then you're gonna get little strips out of this. And let me see if I can try to blow up one of these strips. Okay, so that strip is going to have radius y. And since you are already given your bounds in terms of y, essentially we're going to want to put our function in terms of y inside of our formula. So like here, we're actually going to be putting in just a y, but I'll get back to that part later. And let me do one more thing. Let me color code this a little bit more. Radius y. Okay, so things that we know at this point. Let's also put our bounds in. We know our bounds are given in terms of y. That's from 0 to 1. So we have this part C to D here. Radius y, the y is going to be the part right here. And then the circumference of this little strip, I'm going to put in blue. Would actually be 2 pi times y. Okay. All right, now the next part for ds. Let's see, what other colors do we have here? Let's use green, dark green. Remember ds, you're either going to have ds equaling square root 1 plus g prime y squared dy, or ds equaling square root 1 plus f prime x squared dx. This is kind of your hint of which one you should use. We have our bounds in terms of y, so we're going to want to use the one with dy. Okay. Let me save that. Erase this portion. Okay, so then off to the side, let's find g prime y. That's going to be y plus y cubed prime, which is going to be 1 plus 3y squared. Okay, so then ds is equal to square root 1 plus the quantity 1 plus 3y squared dy. Now, kind of a hint, if you're looking at x-axis rotation or y-axis rotation, still look at the bounds. We're going to use the same ds for both of them because we want our integrand to have y's in them. Okay. Okay. Now, also one thing to emphasize what this ds is doing, right? It's essentially the arc length part. So you're integrating all these little circles the outsides of them, over this strip. Okay. Let me save that. And then let me clear out a few details. Okay, I'm just gonna go ahead and get rid of this. I'll just get rid of all of it. I have it written down. It's easier to just clear it sometimes. Okay, so now remember that S, come on, is equal to integral. We have our bounds, 0 to 1. Don't remember what color I made them. They'll be orange right now. And then the circumference portion is going to be 2 pi times y. Now again, remember in our general formula, we had a y here. Since x is given in terms of y, we're actually going to use radius y as just a y. Okay. You'll see the difference in the next part. And then we have our ds next door. So essentially this portion here, circumference of circular strip, okay, and then over here, over the arc length of shape, the chalice shape. So over this arc length, we're just adding up all these little strips. And then remember, as we take the limit, as n goes to infinity, this number of strips we have, we get an integral from that. So this is what you should have for that first part. Let me save that. And then let me clear it out. I'm going to go ahead and just select this portion and move it for later because I'm going to need the same one. Okay, so let's go over part 2. Which covers y-axis rotation. Remember from our graph, we had a strip that looked somewhat like this. So now we're going to be rotating that about the y-axis. Okay, and then our circular strips are gonna be this way now. Sorry, I know that's a little small. I should have made it bigger. Okay, so blowing up that circular strip. Its radius this time is going to be x. Okay. For y-axis rotation, our surface area will be given from bound C to D. You're going to have 2 pi x ds. As we discussed, it'll be the same ds as before because we want y's in our integrand based on these bounds. The 2 pi is not going to change either, so we just need to figure out what the x portion will be. Now, since you have an x in the formula, but x is given in terms of y, and you want y's in your integrand, you're actually going to replace x with y plus y cubed in formula for s. Okay. So s is equal to, we have our bounds again, 0 to 1 for y. We have 2 pi times x, which is given in terms of y here. And then we have our ds part next door. Okay. So essentially, the circumference part is here, and that's covering the circumference of all these little strips. And then the ds part right here, that's covering this arc length right here from your original function. Okay, let me save that. And then I'm going to clear this. Mm-hmm. Okay, so now for part C, use technology to evaluate the integrals from part, oops, sorry, as I put part A1 and A2, I realized that this should be part B. Okay, so for A1, you had S as the integral from 0 to 1 to pi, y, and all this stuff. So you can just use, I think I used eMath help for this. Or you can also use Wolfram Alpha. Plug that in. For part A1, you get approximately 8.5302. And then for part A2, you had this integral. So same thing, plug it in, and you get approximately 13.5134. That wraps up 8.2 number 5. And now we move on to 8.2 number 8, which is a wee bit longer. All right, let me save that. I'm going to clear this out. So section 8.2, number 8. We want to find the surface area of a given curve. And we have y equals root 5 minus x, with x being between 3 and 5, and its x-axis rotation, which signals to you that you're going to be using s equals 2 pi y ds, and then your bounds will be a to b, since we have bounds given for x. Same thing, graph your curve. For this part, I'm going to skip the chart part. So 3, 1, and 5, 0. Looks something like this. Okay. That's going to be your curve y, which is a function of x in this case. And then we're rotating that about the x-axis. That should actually be a little bit higher up. Sorry, hold up. I will not skip the chart, just to avoid any issue. So the values that I got, I plugged in 3, 4, and 5 for x, and I got approximately 1.41, 1, and 0. So it's more like this. Okay, so y is a function of x. Okay, and then we're rotating that about the x-axis. So your circular strips will look like this. We can blow that up off to the side. You're going to have a radius of y. So that part is going to refer to this y here. But remember, we have our bounds given in x. Which means we are going to be using root 5 minus x in place of y for the radius. And that also means for ds, we want x terms. Okay, so ds will be the square root of 1 plus f prime x squared dx. And that's the part that is going to take us a little bit. So let's just put together what we have so far. S equals, for our bounds, we have 3 to 5 for X. We have the 2 pi still. We discussed why you're going to replace y with root 5 minus x. And then this ds part is going to be here. Okay, let me save. And then I'm actually just going to clear out the entire screen minus this portion because I don't want to keep this much messiness on here. Okay, select this and move it up. Bam. Okay, so now is the really messy part for this particular problem. It's finding ds. Remember that square root 1 plus f prime of x squared dx. So off to the side, f prime of x. Remember, that's going to be y prime. So that was root 5 minus x. And we're going to take derivative of that. So then that would be 1/2 times 5 minus x to the negative 1/2 times -1 from chain rule, which is going to give us -1/2 times 5 minus x to the -1/2. So then f prime of x squared will be that quantity squared. Which gives us 1/4 times 5 minus x to the -1. Okay, which means 1 plus that will be 1 plus 1/4 times 5 minus x to the -1, which you could also write as 1 plus 1 over 4 times the quantity 5 minus x. Okay, now I'm going to go ahead and save this picture. And then I am going to also move this up. And clear. Okay, so ds is equal to, we have square root of all this stuff times dx. And then we're going to combine these into one fraction. So that would be 4 times 5 minus x plus 1 in the numerator, all divided by 4 times 5 minus x, dx outside. And then that's going to be square root 20 minus 4x plus 1 over 4 times the quantity 5 minus x dx, which equals root 21 minus 4x over 4 times 5 minus x dx. And then one more thing for good measure that we can do, just so we don't have to worry about this 4 here. The 4 is essentially square rootable. It's like taking a 1/4 out and then square rooting it. So this is our ds so far. I'm going to go ahead and select this portion. Okay, that did not work. And erase. Okay, so S is equal to bounds 3 to 5 to pi. We have our root 5 minus x. And then we have ds next door, which is 1/2 times root 21 minus 4x over 5x, 5 minus x dx. So first bit, you have a 2 times a 1/2. That's going to turn into a 1, which is beautiful. And then the pi can come outside of the integration. You made the color. Okay. So S equals, you have pi, bounds 3 to 5. We have root 5 minus x. And then we have root 21 minus 4x. We could essentially split this root. You wouldn't have to if you didn't want to write it that way, but it's going to cancel out in the next step. So right here, cancel, cancel. And then S is equal to pi integral 3 to 5 root 21 minus 4x dx. This is going to be a u sub. Let u equal 21 minus 4x, then du equals -4 dx, which means negative du over 4 is equal to dx. And then, just for good measure, you can go ahead and do the bounds as well. If you don't like that, remember you can just leave the bounds off until later. And when you go back into x, you can put the x bounds back. But when x is equal to 3, you plug in here and you get u equals 21 minus 4 times 3, which is 9. And when x equals 5, u equals 21 minus 4 times 5, which would give you 1. So now we have pi bounds have changed. Where there's a 3, now there's a 9. And where there was a 5, now there's a 1. And then we have a square root u, and then negative du over 4. Let me speed up a little bit. So negative pi over 4 on the outside, 9, 1. We have u to the 1/2, and then du. And then you can actually switch the bounds by negating your whole integral. So pi over 4, 1 to 9. If you forgot, it doesn't matter. When you integrate, it'll still work out anyway. Okay. Let me go ahead and save this picture. And then erase. I'm sure there's some easier way to do all this erasing. I'm still figuring all this out. Thank you for bearing with me. You'll be able to fast forward through all this nonsense in the video. Okay. All right. So pi over 4. This is u to the 3/2 with the 2/3 in front from 1 to 9. I'll put a dot, 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 and then s comes out to be 13 pi over 3 when you plug in. Okay, that covers the problems from 8.2. Let me save, and then I will ask you guys if you have any questions in 1 second. Let me pause. Okay, so I realized I actually, oh, that didn't help me. Sorry, Sunny might show up there. I'll cut that out if you don't want that in there, but your name showed up because I didn't switch correctly. Okay, so 8.3. We're going to go over number 2 to start. Hydrostatic force. So a tank is 8 meters long by 4 meters wide, 2 meters high, and contains kerosene with a density of 820 kilograms per meter cubed to a depth of 1.5 meters. Find the hydrostatic pressure at the bottom of the tank, the hydrostatic force on the bottom, and the hydrostatic force on one end of the tank. Okay, so I hope you guys can see that. You can't see anything. Okay, let me pull this. Okay, you should be able to see it now. All right, so this particular problem here. All right, let me do a new share. And 1 sec, let me pause recording and make Zoom. Okay, so for section 8.3, number 2, go ahead and draw out a diagram to the best of your abilities. That was ugly. All right, I don't know what color kerosene is, so we'll just use some orange here. Rho is 820 kilograms per meter cubed. G is 9.8 meters per second squared. And then some other details. We know that the depth of the entire tank is 2 meters. And we know that the length is 8 meters. And we know that the width on the edge, essentially on the side of the tank, is 4 meters. And then this portion here with the kerosene is up to 1.5 meters. So let's start with part A, hydrostatic pressure at the tank bottom. Okay, so remember for hydrostatic pressure, your pressure is going to be equal to rho G times the depth. The part that generally varies, the part that varies for your integrals would be the depth. But in this case, at the bottom of the tank, the depth's constant. Which means your pressure will be constant at the bottom of the tank. So P, that's going to be 820 kilogram per meters cubed times 9.8 meters per second squared. Now for your depth, just be careful here. You're not talking about the depth of the entire tank, right? You're talking about the depth of the kerosene. So that's going to be 1.5 meters. Plug all that in. P comes out to be 12054. The units would be kilograms per meter second squared, which you wouldn't really need to worry about. It's just a good way to check, especially if you're going to be doing physics and things. It's kind of important to know what the units are equivalent to, but those are pascals. Okay, so that's the first part. Let me save this. I'm going to clear the bottom and go over hydrostatic force for part B. Okay, part B, the hydrostatic force at tank bottom. So again, at the bottom of the tank, your depth is constant, which means your pressure is constant, which means your force will be constant as well, partially because your area at the bottom is also constant. So your force equation, remember that's going to be your pressure, your hydrostatic pressure times the area of the cross section you have. So we're talking about the bottom of the tank, which is 4 meters by 8 meters. So your area is going to be equal to 32 square meters. Okay. And then the pressure is actually going to be the same pressure that you used in the last problem because the depth is constant. So force equals, we had 12054 kilogram per meter second squared times your area, which is constant at the bottom, 32 meters squared. And so your force comes out to 385 728 kilogram meter per second squared, and those are newtons. So that's your hydrostatic force at the tank bottom. And then this is when it gets a little bit more confusing because now you are talking about the side of the tank, so your depth is going to vary. Your area in this case actually isn't going to vary, but we'll see in our next problem that it will for some of these. So let me go ahead and clear the bottom again. Let me see actually if I can select all of this. Oops. Select it all and clear it all at once. No, I can't. That sucks. I'm sure there's a way. I'll figure out a way at some point. Not tonight. Okay. So essentially, you can think about we're looking at one of these sidewalls here. Ooh, crap. All right. So for that sidewall, that was ugly. We're gonna have our kerosene up to here. We have two meters here. The kerosene's up to 1.5. And then we're going to be having these little strips. I'm actually going to be using Y for the depth part. So let's first think about our formula. Oh, one more thing, 4 meters here. Okay, so the formula we'd be using for the force set up your Riemann sum first. Limit as n goes to infinity. Sum n equals, I equals 1 to n. And we have the pressure on the ith strip times the area on the ith strip. So for the pressure, P sub I, remember that's going to be rho G, and then times your depth at the ith strip. And then for your area, the area of the ith strip is going to be your width WI, which is right here, times delta, and this part depends on whichever variable you use. I'm going to use Y. So this point here would be Y sub I star, and the width of that strip cannot see that. Strip width delta Y. Okay. So let's start with the depth part. Set up your coordinate system. For this one, I'm actually going to set it so that Y is equal to 0 right here. And positive direction down. X is going to be coming out this way. And then to find a relationship between Y and D, here's what I would suggest if you're still a little confused with this. You're saying, okay, well, what's the relationship between Y and D? Is D actually always going to be equivalent to your Y? No, it depends on how you set up your coordinate system. So when Y is equal to 0, your depth of the kerosene is actually equal to 0 as well. Okay, D equals 0. And then when Y is equal to 1.5, so right down here, what will your depth be? Your depth is going to be 1.5. Okay, so in this case, we see that D is equal to Y. And when that occurs, remember you're talking about the ith strip. So the depth of your ith strip is the same as Yi star. Okay, so what that means is your pressure of the ith strip is rho g yi star. Okay, let me save that. And then let me also make one more mention. When we're talking about the bounds then for our integral, you're looking at the y stuff here. Because remember, that's where you put your coordinate system, right? So y for the bounds, you have 0 to 1.5. And that covers what yi star is between. Okay. All right, let me get rid of some of this. Okay, so what we found so far, pressure is rho g yi star. And so now we have to tackle the area part. Find a relationship between y, essentially your depth, from your coordinate system though, okay? And width. Wi. And I want you to remember that Wi, your width, is actually going to be like in x terms, essentially, right? On horizontal. So I'm actually going to make a relationship between y and x and then change x into w a little bit later. It's just easier for me to see it that way. So for Wi, when y is equal to 0, what is your width? The width is 4 meters. When y is equal to 1.5 at the bottom, the width is still 4 meters. So the width stays constant with respect to depth. So your Wi is going to be 4, which means your area of the ith strip will be 4 times delta y. Let me save this and clear it. Almost there with this problem, y'all. Okay. Ooh, okay, I didn't know that could happen. Learned something new. Here we go. Okay. All right, so now we're ready to set up our integral. Sorry, set up your Riemann sum first. So limit n goes to infinity, sum I equals 1 to n. For pi, we saw that that is rho g yi star. And for a, we see that that's 4 delta y. Okay, so what your integral becomes, you have your bounds. I don't remember what color I made them. Orange works. 0 to 1.5. Kerosene bounds, right? And then you're going to have your rho G. Yi star will become Y. And then delta Y becomes dy. Okay. So your force integral, 0 to 1.5, 4 rho G Y dy, which turns into 4 rho G 1/2 Y squared from 0 to 1.5, ... which equals 36162 newtons. Okay, do me a favor, save any questions you might have until after we get through number 8. And then I think once we're done with number 8 and they answer some questions about this, we're just gonna hold off on doing the center of mass problems until next time. Let's see. Let me go ahead and save and clear. And then let me share with you guys our next problem. It's number 8. Okay. The prompt tells us you have this vertical plate submerged or partially submerged in water, has the indicated shape. Explain how to approximate the hydrostatic force against one side of the plate by Riemann sum. You don't have to explain it in words, you just make the Riemann sum. And then express the force as an integral and evaluate it. So number 8 is right here. All right, let's go back to the whiteboard here. Load that up. Okay. All right, so we have section 8.3, number 8. Here's our diagram. So we've got water up top. And then there's 4 meters of water above your shape, which is a triangle. Okay, the bottom of this triangle is 6 meters, and the top of the triangle to the bottom of the triangle is 2 meters. Okay, so we are looking for the hydrostatic force on plate. Remember your formula, F equals limit n goes to infinity, sum I equals 1 to n, P sub I. A sub I. Okay. And then remember P sub I is rho G D sub I. And A sub I is WI delta X. Oh, sorry, in this case, I'm still gonna call it Y. I know your book calls it X sometimes when you're going in the vertical direction, but a lot of the videos I've been seeing, and the easiest way for me is just to keep it as Y if you're going vertically, okay? All right, so we're going to need to find DI, and we're going to need to find WI. let's start with DI. I'll just put depth. Okay, so this is that thing where you really need to choose your coordinate system where you're going to put everything. I am going to put y equals 0 right where the top of the triangle is. Okay, and then I'm going to have my coordinate system going down in the positive direction. So right down here, y would be equal to 2. Let's compare the actual depth of the triangle in the water to our coordinate system. So right here, hopefully you're seeing that the depth would actually be 4 meters. Okay, and then here, the depth would be equal to 6 meters. So when the depth is equal to 0 meters, what would that mean about y? That means y is equal to -4. So when y is equal to 0, d is equal to 4. And when y is equal to 2, d is equal to 6. So the relationship between these, because it would be a linear relationship, you're going to have a d equaling y plus 4. Okay. And you can check that, right? Like, okay, well, d, hopefully you're seeing that it's going to be y with 4 added. Go ahead and put a sub I and a sub I star. Okay, so see how we found a relationship between d and y? All right, between our depth and our coordinate system for the depth. All right, so we have DI, and that means that our pressure, PI, will be equal to rho G times YI star plus 4. Okay. And then go ahead and think about your bounds now. Okay. Where does the, essentially, where's the top of the triangle? Where's the bottom of the triangle in terms of submersion? Well, we're using y, not d here, when we plug into the integral later, right? So we're going to want to use 0 to 2 with yi star in between. Okay, I'm going to take a picture, save that, and then I am going to clear this and we're going to look for wi. Oh, come on, man. Like when it would be faster to just rewrite it, you know? All right, so that's what we found so far. Okay, so now for the area, find your relationship between your y and your width. Okay, coordinate system y, which represents your coordinate system depth. Okay, so You can make your little strip here. That is width delta y. And then this point here would be yi star. And the width would be wi. Now there's actually two ways you can do this. I like the second method I'm going to introduce for you a little bit better because I think it's a little more clear in terms of understanding, but the symmetry way might work better for you. So I'll put method 1, symmetry. So you have this triangle and you are going to be comparing your depth. For me, it's easier to look at half the triangle. You don't have to. You can if it's easier. If you're not sure, just ask me. Okay, so for the strip, let me do this. That'll be our small triangle. We have a wi over 2. And the height would be yi star. And that would be similar to your larger triangle. This would be half of 6. And then this distance would be 2. So then what we're saying is, okay, well, wi divided by 2 is to yi star what 3 is to 2. Cross multiply and all that good stuff. And you wind up getting a wi equals 3 yi star. There's your relationship between y and, remember this is kind of like x, but it's your width. So how does w vary as y varies? Essentially, wi varies linearly with depth. Okay, let me save. And then I'm going to show you method 2. We're going to find out we get the same thing for wi. Okay. So method 2. It might not be intuitive to you, but that's why I would definitely say watch that video I posted with the different types of hydrostatic force problems so that you can start to see when does width vary linearly with depth, when does width vary constantly with depth, and so on and so forth. The width here, again, varies linearly with depth. So for the width, I'm going to use x. For the depth, I'm going to use y. And then linear relationship means that y equals mx plus b. Okay, so then I say, well, what's the relationship between y and x? When y is equal to 0, what would the width be? 0. And when y is equal to 2, the width is 6. So from here, find your slope m. Okay, and then plug in, these are points, right? Plug in one of these sets of points to this equation to find out what b should be. So 0 equals 1/3 times 0 plus b. That means b is equal to 0. So y equals 1/3 x. I'm going to save that and erase. Okay, now remember y is representing your depth, but from your coordinate system, you can go ahead and replace y with yi star. You have 1/3, replace x with wi and solve for wi. So wi equals 3y star. Same thing. Okay, let's wrap this one up. We found our di, we found our wi. I'm gonna clear this out. Okay. So area of the ith strip will be 3 yi star delta y. So our force equal to the limit as n goes to infinity, summation I equals 1 to n. We have P sub I as rho g yi star plus 4. And we have area as 3 yi star times delta y. That will turn into integral from 0 to 2. Okay. Rho g y plus 4 times 3y dy. Okay, and then that's going to be 3 rho g integral 0 to 2 y times y plus 4 dy. I'll just keep it on the same page. Y squared plus 4y dy. Save. Erase. Okay, so that equals a 3 rho g 1/3 y to the third plus 2y squared from 0 to 2 dot dot dot. Force comes out to be 313,600 newtons. Save. And yes, that is going to wrap up this portion for today. Let me go ahead and save this and then stop recording.